All right. Atomic structure 11. We're talking about isotopes today. And what are isotopes? So I'll give a basic definition of isotopes. Very simple. So in the nucleus of an atom, you have protons and neutrons. And if they're a different amount, if they're not equal, if they don't have the same amount, then it's an isotope. In other words, if there's more neutrons than protons, it'll be an isotope, and vice versa. And when we look at the periodic table, the majority will have more neutrons. Only helium-3, I'll talk about helium-3 later, only helium-3 has more protons than neutrons. And what I mean by that, I mean the only stable one. There are unstable isotopes that have more protons. So I'll talk about helium-3 later. So again, the majority, when you're looking at the periodic table, you will see more neutrons than protons. And all elements on the periodic table have isotopes. In fact, gold has 41 known isotopes. So again, an isotope, when it's not balanced, when there's more neutrons than protons, or vice versa. All right, let's get a clean page here. So let's just start with oxygen. Why not? So let's get our pen ready. What color should we use today? Why don't we use green? Let's use green. So if I say O2, O2 is a molecule, and it's a molecule of two oxygen atoms together. That's why it's O2. There's that subscript. Now, when we're talking about isotopes, we're going to use a superscript. So let me just write that down. That's a subscript. And again, sub means under in Latin, like subway. And then we're going to have a superscript. And I'll just put a superscript there on the left, not on the right. So when you see that, we know we're talking about the number of the atomic mass, that is, of that element. For example, let's start with oxygen. So when we have oxygen, oxygen has 8 protons and 8 neutrons. Therefore, its atomic mass is 16. Now, we know neutrons have a slightly heavier mass than protons, but we're just rounding this to 16. So that's why it's called oxygen 16. It'll be written like this: oxygen, with a little dash there, 16, oxygen 16. And we can write it this way also with the superscript on the left. For example, if I said oxygen 17, how would you write that? Well, it would be the symbol oxygen and the 17 in the superscript on the left, not on the right. That's oxygen 17, and it'll have 8 protons, but 9 neutrons. You see? And so again, when we're talking about isotopes, the majority they'll have more neutrons. And we'll talk about helium-3 in a minute. So what if I wrote this? What is this? What is that? Well, that's oxygen 18. And again, it will have 8 protons, but 10 neutrons. And those are the isotopes of oxygen, even though oxygen 16 is just a regular atom, if we want to use the term regular. Because if we look at the periodic table, the majority of the periodic table are isotopes to begin with. All right. And we know that the O2 that we breathe, we're actually breathing in 2 molecules of oxygen, and it is the oxygen 16, because oxygen 16 makes up 99.7% or more of oxygen that we have, not of the atmosphere, because we know nitrogen makes up the majority of the atmosphere. But of the isotopes I listed here of oxygen 16 there's 99.7% of it compared to the others. All right. And I did mention that if you look at the periodic table, if you look at the atomic number and the atomic mass, you'll notice that there are more neutrons as you look throughout the whole periodic table. Let's look at this. Let's use red. It'll stand out. So here we have hydrogen, and we'll talk about there are different types of hydrogen isotopes. There's 3 we'll talk about in a minute. But if you think on the periodic table, this number here, this is the atomic number, and it's usually written with a Z. Because Z, I'll write it over here, Z is a German word, Zahl. So also some people write Zahlen. And that just means number. In this case, they use Z for the number of protons. So Z equals the atomic number. So the atomic number is the number of protons. And you also may see that symbol Z because C, not C, but Z is an integer in mathematics. An integer is any number that's not a decimal or fraction. So we're going to use Z with a plus because we know protons have a positive charge. In math, though, if you see a Z plus, we're talking about numbers that are greater than 0, right? Because you can also see this in mathematics. Those are negative numbers because we know negative numbers, negative whole numbers, are also integers. So here is, again, if we look at this chart here, we know that hydrogen has 1 proton and it has no neutrons. So that is an isotope. But there are 3 isotopes of hydrogen we're going to talk about. So here we have helium, and we'll talk about helium-3, but you see it has 2 protons, 2 neutrons. But lithium has more neutrons right away, so we know that's, let's just put a check there, that's an isotope. Beryllium, right? Boron. Let's go down the list, right? Here, fluorine, keep going, sodium, aluminum. Your aluminum foil is an isotope, right? And again, when we're looking at this list, there are many isotopes for each element. And then we got phosphorus over here, chlorine, argon, potassium. And if we just keep going, you'll notice there's more isotopes than what we can say, quote unquote, normal atoms that have the same amount, even though we don't use that term normal. And if we keep going, we'll just do a few more, right? Well, here's nickel. We got nickel. See, it has more neutrons. Copper has more. Gallium has more. Arsenic has more. I'm just randomly putting in. We have krypton and more, and you just keep going. You can see there's more neutrons than protons, and that's necessary because you really need, in some cases, more neutrons to stabilize the protons. Because remember, protons have a positive charge, and they want to be away from each other. So neutrons are like those babysitters that keep them in place. So here's a Bohr model of oxygen. And what type of oxygen should I write for this? Let's use blue. Start with blue. So if I say O, what should be the superscript here, this number? Well, this should be oxygen 16, right? And this is the oxygen we normally breathe, right? Because it's 99.7% of the oxygen that we have. But if another neutron was in here, and it was 9, right? Now we have more neutrons than protons, and then we have oxygen 17, and there's also oxygen 18. Okay, let's go to hydrogen now. So here's hydrogen, and hydrogen is the only element that names its isotopes. The other isotopes just have the name with the number, but hydrogen names them. And so the hydrogen that we're used to, and we'll change the pen, go back to red, is protium. Protium is the hydrogen that is in most abundance. It's the hydrogen we'll use for water. So if we mix we're actually mixing protium with oxygen. So we use H2. When you see H2O, when you see that compound, right, there's that subscript right there. There's that subscript. We know we have 2 hydrogen molecules and 1 oxygen molecule. So that's water. That's dihydrogen monoxide. That's the fancy name for it. And it's from actually protium, because protium has a proton and an electron. It does not have a neutron. So if it doesn't have a neutron, it's still considered an isotope. Deuterium over here, we can use deuterium. You see deuterium has 1 neutron. It's a little blurry. So it has 1 proton, 1 neutron. And you notice over here, the atomic mass is on top and the atomic number is on the bottom. That's when if they put a symbol in, you'll see that like that. And then deuterium, by the way, is also called heavy water. And they use it in nuclear reactors to cool down, well, actually to slow down neutrons. So you don't have an explosion in a nuclear reactor. So that's what deuterium is for. And there are reports that maybe you can drink it, but I would not drink it. If you can get a hold of it. Some people say you can drink a little bit of it. Tritium. Now, tritium is also an isotope of hydrogen. Notice it has 2 electrons and 1 proton. And tritium, by the way, is radioactive. Radioactive. So again, these are isotopes of hydrogen. We usually don't say protium, we just say hydrogen. But deuterium and tritium are isotopes of hydrogen. And again, hydrogen is the only element that names its isotopes. And here are some isotopes of carbon. We have carbon 12, right? That's the carbon we see on the periodic table. It has the same amount of protons, same amount of neutrons. Carbon 13 has 1 more neutron, and carbon 14 has 2 more neutrons. Carbon 14 they use, and let's get a pen going, they use in carbon dating. When you see that carbon dating method, you might have heard about in college or school. If we want to date bones, anywhere between 500 to maybe 56,000 years, we can date how long or when did those bones live, within a certain percentage. So carbon 14, and I'll explain that, it comes into we have carbon 14 in our body, and when an organism dies, the carbon 14 will start decaying. It'll decay into nitrogen 14, and then scientists can use that decay rate to determine how old the bones are. So carbon 14 is a dating method, and it is also an isotope. And like I said in the beginning of the video, helium-3, as you can see here, see that superscript on there? Just keep that color one out. So this is helium-3. It's very rare. Capital letters. It's very rare. And it could be used in cryogenics. I'll write the word cryogenics. Cryogenics. You may have heard about cryogenics. We do not have the technology as of now, but in cryogenics, we will freeze people, or you can freeze things, and hopefully in the future we can unfreeze them, thaw them, and we would be able to cure them if they had some kind of disease. Or let's say we're going on a trip to Betelgeuse or Alpha Centauri, we can freeze ourselves, and then when we get to that destination, which could take 80,000 years or much longer, then we can unfreeze or thaw ourselves out. But we don't have the technology now, but that was cryogenics. And helium-3 is that element we would need for cryogenics. But it is extremely rare. And helium-4, this is just the helium that we see on the periodic table, right? Its 4, atomic mass is 4. It has its 2 protons, 2 neutrons, and 2 electrons. And we had a few students ask about, can an isotope be an ion? Of course. Yes, they could be an ion. Remember, the majority of the periodic table you'll see are isotopes to begin with. So yeah, it's like chlorine 35. So, and let me get our pen going. Chlorine 35, which actually should be a superscript like that. There's chlorine 35. If it has an ion to it, we'll put a negative to it. And if it's, let's say, a positive, right? So now this is a isotope because it has more neutrons, and it's also a positive ion because it has more protons than electrons. So yes, isotopes can be ions. And then just one more thing, if you're thinking about in social studies or in history class, you may have heard of uranium. Uranium is radioactive. They used it in the atomic bomb and the Manhattan Project, but they actually had to get uranium-235. They had to enrich the uranium to get uranium-235. And so we know we would write it as 235U for uranium, and that is an isotope. So it has 92 protons, 92 electrons, but 143 neutrons. So it's very unstable, very radioactive. And again, just a review, if we're using letters, you would see a Z, right? Because that's the atomic number, Z for Zalin or Zal, the electron and the neutron. All right, so that is isotopes today.